All right, everybody. Recording has started. So let's take a look at the next part. The outline that I gave you today deals with orbital filling, or orbital diagrams and electron configurations. Over the past couple of days, we talked about the quote-unquote location of electrons in the quantum mechanical model. Why do we have location in quotation marks as it relates to the quantum mechanical model? Ben, go ahead.
Because it's more like a probability aspect?
It's more of a probability aspect. It's not the actual location of electrons. It is the most likely place where we could find them. But the possibility still exists that they could be anywhere. Okay? We gave those areas of high probability a name in general. What did we call those areas of high probability?
Main energy level?
Those are actually
Oh, quantum, principal quantum number?
not exact. That's part of it, but
Electron clouds?
yes, but
Principal energy level.
yeah. So that's part of it. In general, not that one. In general, we call, where is it? There we go. Good Lord. So, in general, we call those areas of high probability of finding electrons orbitals. Okay? Those are the areas of high probability of finding electrons. Now, is there only one area of high probability of finding electrons around the nucleus? Some more than others, but there's lots of different areas where electrons show up. But there's lots of different areas where electrons don't show up. So, in general, we refer to these areas of high probability as an orbital. That's a little different than what Bohr introduced, right? What did Bohr say about electrons back in his original model back at the beginning? Go ahead.
He said that they have to stay on a certain ring.
So we refer to those as orbits, right? But these are orbitals, right? It's not the exact area, but a general area of high probability. Does that make sense? And then yesterday we talked about, how do we characterize those areas of high probability? That within this picture, right? Within this picture of the quantum mechanical model, there's areas that show up more dark than other areas and principal quantum levels, and then within those areas, sublevels and stuff like that. Okay? What we're more interested in is, okay, all of these areas exist. There are areas that it's highly probable that electrons will be in, but is there an order to which we fill them up? Are there certain areas where it's more probable of finding electrons than other areas? And we find out that the answer to that is yes. What sort of governs that idea? What determines what areas are more probable of finding electrons than other areas? We kind of talked about yesterday, there were a couple things going on. What sort of tells us where electrons are most likely to end up? So, take this picture. So, here's this picture. If you had to place a guess where the most likely location for an electron would be, where would you make that guess? All right? Dolly, go ahead. This section right in here? Why would you make a guess about that section right in there? Close to the nucleus, that's one reason. Nico, what else?
It's the first orbital.
It's the first orbital, yes. What is that? What do you want to add?
There's usually an electron in the first orbital.
That's true. There's a reason why that is, though.
Because they like to stay at a low energy level.
Okay, this is lowest energy, right? Closer to the nucleus, lower energy. As we get farther away from the nucleus, the energy of those electrons will increase. But we talked about the past couple of days that lower energy nature favors lower energy states, so those electrons will gravitate towards those lower energy states. Do you have something else you want to throw in there? Okay. Let your hand go still. All right, good there? That leads us to orbital filling and electron configurations. There is one rule that sort of takes us through all of these things. I know it's a white background, but we're going to be doing a lot of writing today, so there's not a lot of like copying things down. And that rule is called the Aufbau principle, named after a guy named Aufbau. The Aufbau principle states, orbitals are filled from lowest energy to highest energy. I hope that that makes sense based on our discussion of the last week or so, right? We said that nature favors lower energy states, so the orbitals, those areas of high probability that represent lower energy, are going to get filled up first, because that's where electrons tend to gravitate towards. As we've discussed over the past couple of days, right, orbitals closer to the nucleus contain lower energy. Just like that idea started with Bohr, even though we modified Bohr's idea, the thought that lower energy closer to the nucleus still remains. So the orbitals that are closest to the nucleus contain lower energy. Oh, sorry. Good there? Got that filled up? All right. The next thing that shows up in your notes is an orbital filling diagram. If you look at the one on the left, I think the one on the left is a little easier to read, so we'll probably use that one a little bit more often. But it's not on page 147 of your book. Sorry, that was an old book. So. But this picture, this chart on the left, if you look at the y-axis or over on the far left edge, what does it say along the far left edge over there? All right? Go ahead, John.
Increasing energy of electrons and orbitals.
Increasing energy of electrons and orbitals. So where are we going to start this chart? Where are we going to start using this chart? Ben?
Where the lowest energy is.
Where the lowest energy is. So bottom or top, Ben? Bottom, because like the arrow points up, increasing energy, blah, blah. So this chart is going to start down at the bottom, okay? One thing that we discussed yesterday, but to make sure that we review, we said that orbitals are these, we call these areas of high probability orbitals, but that each orbital can only contain a maximum of 2 electrons. Why did we say that there won't be a whole lot of electrons filling the same place around the nucleus? Go ahead.
Because since electrons have the same charge, they repel each other.
Electrons have the same charge, so we won't find a whole bunch of electrons in the same place, right? As a matter of fact, those orbitals, those areas of high probability, we can only contain 2 before that spot is filled, and those electrons will now have to go find another place to settle. Good so far? All right. This orbital diagram, or this orbital filling diagram, we're going to keep coming back to as we go throughout the day. So let's talk about an orbital diagram. An orbital diagram shows the distribution of electrons within orbitals. Orbital diagrams will show the distribution of electrons within orbitals. Depending on what book you look at or what text you're reading or whatever it is, some orbital diagrams will be circles, some will be lines, some will be boxes, but they all represent the same thing. They represent these different orbitals that exist around the nucleus, these areas of high probability. So depending on, and then we use arrows to represent single electrons. So you might see orbital diagrams that look like the ones over there on the left, where they have a circle and then they might have 1 arrow inside of them or 2 arrows inside of them, depending on how many electrons are there. Sometimes you might see just single lines drawn to represent the orbitals themselves, and then these arrows represent electrons. But most importantly, right, the first thing, showing the distribution of electrons within orbitals. That's what we're trying to accomplish with the orbital diagram. Okay? Good there? All right, ready to give it a try? So let's start off with hydrogen. This is where the this is where your periodic table is going to come in handy. Let's go here first. So starting off, orbital diagram for hydrogen. First thing we have to do, if an orbital diagram shows us the distribution of electrons within orbitals around the nucleus, we have to know how many electrons we have to place, how many electrons we have to show. Where are we going to find out the number of electrons that we have to show in our orbital diagram? Where are we going to find out how many electrons we have to put in? Haley? Periodic table. Specifically, what part of the periodic table will tell us that?
Atomic number.
The atomic number. Good, Haley. Well done. Good vocabulary usage and everything, right? So the atomic number actually tells us what, Haley? What does the atomic number actually tell us?
The electrons and.
It actually tells us the number of protons. But in a neutral atom, that also has to be the number of electrons as well. Okay? So, if you look on your periodic table and you find hydrogen, okay, that one's pretty easy to find. It's up in the top left. What's hydrogen's atomic number? 1. So that means how many electrons do we have to place here when we're drawing this orbital diagram for hydrogen? Just 1. So we have to place 1 electron. Okay? So you go to your orbital filling diagram that's on the front page of your outline, which just so happens to be the same page we're still looking at. And Ben, we said, where are we going to start on that orbital filling diagram? On the very bottom. So you start from the bottom, Ben, and what's the first orbital that you come across? What's the first thing that's labeled on that picture?
S orbital.
The s orbital, but specifically which s orbital?
The
What principal energy level is that s orbital in?
1.
1. So the first orbital that we come across is the 1s orbital. Because it's an s orbital, what can you tell me about it? Do you remember from yesterday? Yeah? It's a sphere, right? It's close to the nucleus because it's the first energy level. It's a spherical shape around the nucleus. That's an area of finding electrons. It's an area of high probability. Why? Where does it show up on that energy diagram?
At the bottom.
At the bottom. That means it has low energy. So that means there's a high probability of finding electrons there. So here's what we do. However you want to do it. Circles, boxes, lines. I don't care. Lines is the way I do it because that's kind of the fastest. So you draw a line like that. Okay? And then you label that line with which orbital it is representing. So which orbital did we say was going to fill up first? 1s. So you write 1s underneath it. And then we use arrows to represent the electrons. So how many electrons did we say we had to place here in this diagram? Just 1, so we draw 1 arrow. Okay? Now, as far as drawing arrows go, when you do orbital diagrams, sometimes they get tedious after a while, so we do some things to make them go a little faster. A lot of time, you'll see them written just with like one side of the pointy part like that. Okay? Perfectly fine. If you want to draw it as a full arrow, that's perfectly fine too. Okay? Doesn't really matter. So we use that to represent the orbital diagram for hydrogen. Hydrogen has 1 electron, and we're most likely to find it in the 1s orbital, because that's the lowest energy place. Good there? Questions?
Wait, what is the one medium and what's that minus?
This is how many, this 1 electron, because
Yeah,
hydrogen,
what's with like the other, like this, that little line above that?
It's a minus.
that's a minus sign, because
They
electrons are
different
negative charge. We use that to represent electrons, right? All right, we're ready to increase degree of difficulty a little bit?
Yes.
All right. So, not too much, but, you know, we'll go from there, okay? So, next, the orbital diagram for, not hydrogen this time, but helium. So, you look on the periodic table, find helium. It's way on the other side. What's helium's atomic number? 2. So that means how many electrons do we have to place here? 2. Okay? So we got to make sure that we account for 2 electrons. Okay? Before, I told you, when we talked about it yesterday, and then I just put it up on the board as well, how many electrons can each orbital hold? 2. So we start back on our orbital filling diagram. right? This one. And Ben, you already told us, right, the first one that we come across is the 1s orbital, okay? But in our orbital diagram for hydrogen, is the 1s orbital full? No, it's not. So if there's some extra space there, and it's the lowest energy orbital, where do you think that second electron in helium is going to go? In the 1s orbital. So we draw the line, we label it 1s, okay? There's our first electron, okay? But here's where it gets a little different. Even though they're in the same orbital, and they're the same energy, they're not the same electron. So we have to distinguish between this electron and the second electron. The way we do that is we draw another arrow, but we draw it pointing the opposite direction. So this one will look something like that. Okay? This idea of distinguishing that electron from this electron is something that we call the Pauli exclusion principle. The Pauli exclusion principle states that each orbital can only contain 2 electrons, and these electrons have to be distinguished from one another. Remember yesterday at the end of the period we introduced the spin quantum number. That was the last quantum number that we introduced. We said that even though those orbitals may have different parts, we have to distinguish one part from the other. This is how we do it in an orbital diagram. One arrow up, one arrow down. Good there? Okay. All right. Next orbital diagram, lithium. So let's look at the orbital diagram for lithium. First, you find lithium on your periodic table. What do you find out about lithium? How many electrons do we have to place in our orbital diagram for lithium? Okay. 3, because that's lithium's atomic number, so we have to take care of 3 electrons. What's the first orbital that always gets filled in every atom? 1s, because it's the lowest energy. So, line, 1s. One arrow up, one arrow down. That's how many electrons? Each arrow represents 1 electron, so that's 2 electrons. Are we done with our orbital diagram for lithium? We are not, all right? So you go back to your orbital filling chart on the front page of your outline. What is the next lowest energy orbital that we run across? Willie? 2s. Okay? So, Willie, how are we going to do this here?
Make another line.
Make another line. What am I writing underneath it?
2s.
2s. I'm going to write that underneath it. Okay? Then, how many electrons do I have to fill?
1.
Just 1. There you go. Okay? That good? Okay? The next orbital diagram that we come across, okay, actually, well, the next one on your periodic table is going to be beryllium, number 4. What's beryllium's orbital diagram going to look like? I'm just going to fill in the other electrons, okay? But let's jump ahead. Let's skip one and let's go to boron. So, find boron on the periodic table. Atomic number what? 5. So that means that we need to place 5 electrons. Okay? So, starting off, where do we always start off? 1s. Line 1s. It's the lowest energy orbital. It always gets filled first. 1 electron, 2 electrons. 1 up, 1 down. Okay? Willie, the next orbital that we came across in our orbital filling diagram was what?
2s.
2s. Line 2s. Oop, 2s. Okay? 2s can hold how many how many electrons? 2 electrons. So 1 arrow up, 1 arrow down. That gets us to what? 4. Okay? If you look at your orbital filling chart on the front page of your outline, what is the next one up? Okay? Here. 2p, right? It's in the next column, but that's the next lowest one. That's the next one closest to the bottom. We understand? Right? We go here, right? Going up, right? Here's 1s, here's 2s, the next one up is 2p. Okay? That's the next lowest energy. That means what? If that's the next lowest energy orbital, that's the next one we're going to fill up, right? Because electrons fill from low energy to high energy. Good there? Okay. So, the tricky part now is, how many p orbitals are there? Nope. Look on your drawing. How many lines are on that orbital filling chart? How many orbitals are there?
Oh, 3.
There are 3 orbitals. There are 3 2p orbitals, right? Look, 2p. Oh, not that one. 2p. 1 line, 2 lines, 3 lines. If you look at your notes from yesterday, there's 3 pictures of p orbitals. We said one goes on the x-axis, one goes on the y-axis, one goes on the z-axis. Does that sound familiar from yesterday?
Yeah.
So, the next orbital that we draw is 2p. But, like it says in your chart, how many 2p orbitals are there?
3.
There are 3 of them. That means you draw all 3 of them. Okay? How you go from here, I really don't care. It really doesn't matter. Technically, we probably should label them all as 2p. Okay? But if you get lazy, you can kind of go like that if you want to. Okay? There are 3 2p orbitals. How many electrons do we have to place? 1. Does it matter where we put them? No. If you look on the chart, right, they're all at exactly the same height as one another. It's not that one of the 2p orbitals has lower energy than the other 2p orbitals. They're all the same energy. So it really doesn't matter where we put that electron. Generally, we just fill it in the first one that we've drawn and that we go on with our day. Okay? Is that good for now? Okay. Next one, though. The next one that we run into is carbon. All right. You find carbon on the periodic table, and what do you find out about carbon? How many electrons do we have to place? 6. 6 electrons. So, I think you're probably getting to see the pattern now, right?
Yeah.
We start off 1s, 1 electron, 2 electrons. Then 2s, 3 electrons, 4 electrons. We have how many left to place?
2.
2 more to go. We said that the next energy orbital that we find is the 2p. But if you look on your chart, how many 2p orbitals were there? 3 of them. So 1, 2, 3, 2p, 2p, 2p. 2 orbitals left. 5. But where the 6th one goes is determined by something that we call Hund's rule. Hund's rule says, if you have orbitals that have equal amount of energy, electrons will not pair up until they're forced to pair up. Okay? Because, what did we say about all the electrons? They repel because they all have negative charges. So we won't see electrons pairing up in orbitals, even though each orbital can hold 2. We won't see them pairing up until they absolutely have to. So when I have to draw my 6th electron here, do I draw it in this orbital right here? No. It's got to go somewhere else. Does it matter where else it goes? No, because either one of these is exactly the same energy, so it doesn't really matter. Generally, we just fill in the next one over, but it really doesn't matter. Okay? Hund's rule. Electrons will distribute themselves as evenly as they can until they're forced to pair up. Why? Because they all repel each other. So they want to try and get as far away from each other as they can for as long as they can. Okay? Good there? Okay, let's jump ahead. What's the next one you guys have on your outline?
Neon.
Neon? Okay. let's do one. Let's do oxygen real quick, okay? Because oxygen's not on your sheet, so if you want to do it like on the side or something like that, or in the margin, okay? Let's do oxygen real quick. How many electrons does oxygen have if you look on your periodic table? It's 8 electrons, because that is oxygen's atomic number.
Wait, why we put down that carbon is 6 electrons?
Because carbon's atomic number is 6. Did you find it?
Yeah.
So oxygen, 8 electrons. First orbital we draw, 1s. 1 electron, 2 electrons. Next orbital that we find, next lowest energy orbital, 2s. 3 electrons, 4 electrons. We said the next lowest energy orbital that we find are the 2p orbitals. But how many 2p orbitals were there? 3. 1, 2, 3. They're all labeled 2p, 2p, 2p. Now, do you have to fill them in the way that I'm going to show you? No. If you get the end result, I really don't care. But watch how I fill the arrows in, right? I've already placed 4 electrons in the 2 lowest energy orbitals. I got 4 more to go. So, 5, 6, 7. According to what? What did we just discuss? We call this Hund's rule, right? That's how the next 3 will fill up. But how many do we have left to place?
1.
1. So we have to fill one more, or one more electron in one of these 3 orbitals. Does it matter which one we actually pair them up in? It doesn't, okay? But when we write that 8th or electron, what do we have to make sure that we do?
Draw it down.
It's got to be upside down. So it really doesn't matter where you put it. Usually we put it in the first one, but it really doesn't matter. Okay? At this point, even though this electron is now in the same orbital with another electron, and they repel each other, which is true, okay? But the advantage of being at the lower energy location is better than the repulsion that it feels from the other electron. Does that make sense? Okay. Here's what I want you to do, okay? Page 2, page 3, and the top, page 2 and 3 are all orbital diagrams for different elements, okay? For homework tonight, I'd like you to try and finish up those orbital diagrams on page 2 of your outline, and then on page 3 of your outline. Page 4 gets into electron configurations, which we haven't discussed yet, which means I probably won't include that on your test, because we're supposed to review tomorrow, but they are important, so we'll probably talk about them like on Friday. Okay? The last page of your outline, Macy, is about electron configurations, which we haven't discussed yet. It's a shorthand way of writing the orbital diagram, but I probably won't include it on your test because we won't have officially introduced it. Okay? So, tonight, for homework, finish up the outline, page 2 and page 3. Orbital diagrams for all the rest of those elements listed on page 2 and 3 of your outline. Okay? Good job today, everybody. And then you can listen to yourselves for recording tonight if you really want to.
Yay.